go ahead and get started with your talk.
Very good.
Dante Schiavo he's currently in Buenos Aires, Argentina. He's a full professor, and he heads the Center for Complex Systems and Brain Sciences at the Universidad Nacional de San Martin, which I hope I didn't butcher too bad. And I didn't realize, but you also had a stint a number of years ago. So you were in the US for a while. And you were, before I got to Albuquerque, you were at the Santa Fe Institute for a few years. So that's an overlap that we had almost. You were there a few years before I was. And he also spent time as a professor at Northwestern University in Chicago and UCLA, and then has since returned to Argentina. So Dante studies dynamics and in particular issues related to criticality. And he's going to share with us some really interesting approaches and results. And we're looking forward to the talk and the subsequent discussions. So thanks so much for joining us. And without further ado, I will go ahead and pass over the baton to you to get started with your talk. Thanks, Dante.
Great. Thank you. Thank you for the introduction. Thank you for the invitation. It's really very nice. It's a pleasure to participate in this initiative. I think that we need more activities like that.
Mm-hmm.
We need more brains. We need more opportunities.
Try to stay connected.
Stay connected, yes. As you said, I'm going to be talking today about criticality, and actually the Southwest is responsible for that. Because my years at the Santa Fe Institute, mainly with all these people that have been very inspirational for the last 25 years, working in the same stuff. So let me share the screen.
Okay.
You tell me if I'm doing the right thing. So we have to use the screen number 2, and then I have to start.
Yeah.
Okay, so so did you see everything's fine?
Looks good.
Okay, so this is a rather general title of what I'm going to be talking about, which is, as Vin says, I study dynamics, and especially dynamics of complexity, and I'm going to try to make the connection between what we call complex or complexity and what is known as critical or phase transitions or criticality. And as Vin says, I studied this for a number of years around biological function. You have here several examples of stuff that looks complex, and like the brain, like proteins, like mitochondria, like even a lipid bilayer. So this is a general outline of what I intend to do in this presentation. Today, I'm going to start trying to give you a sense of not the technical aspects of how you calculate this and that, but rather the intuition behind why we're doing what we're doing. And all the technicalities are in the papers. You can ask later. But I choose the tone of the presentation to be able to transmit, as I said, why we're doing this. The beginning is going to be a 10 minutes manifesto for the non-conoscenti on life is always found near some mix of order or disorder. Always is something need to be not too rigid, but also need to be not very, very flexible, to be in between. So you choose your area of interest, and you will see that life is always in the middle. And we apply these ideas to brains, to proteins, to mitochondria, to social behaviors of insects, to cell motion, etc., etc. At the end, I will summarize and take questions, but today I'm going to be limited to brains. So this is a first slide to sort of, this is the mantra, stuff that I keep repeating. Complexity in nature is associated with a phase transition. And if you believe in that, if you're a physicist, you will immediately understand what is this cartoon here. You have a gas, you have a crystal, you can have a gas, you can have a liquid, and you have, as a function of some parameter, you go from disorder, to order dynamics, okay? Like a crystal or like a liquid. And if you measure somehow complexity, complexity will be always peaking at the middle. Why? Because the gas is all the same. You have a law for locality, and it's going to be exactly the same everywhere. It's going to be boringly the same. And if you go to a crystal, the same. You will be boringly ordered. In between, you have this. And so the point is that for a number of years, people understood in physics that as a function of a single parameter, the same simple laws can originate simplicity, meaning a gas or a crystal, and complexity, something in between. And the moral of the story, and that was relevant for neuroscience and biology, is that we don't need, if we think that our system works like that, to elaborate new laws or complex laws or ad hoc laws to study complexity in nature. So more or less the chronology of this is the diagram that I show you was presented in 87 by Hans Frauenfelder. Frauenfelder still goes to the office in Los Alamos National Lab, and he's 93 years old. He's here, the picture. One of the early physicists interested in protein dynamics. He was the author of this Live Brain Language Protein Turbulent Glasses, in 1987. Around 1980, the intuition that this was true was there. In the 90s, this person here, Per Bach, started, hammering the idea that there was something self-organized around criticality. He studied the theory together with two other people, Kurt Wiesenfeld and Chao Tan. And he was responsible to start convincing biologists, including myself and other people, to study the possibility that self-organized criticality was the source of complexity in nature. Nowadays, we don't only have intuition theory, we have a lot of experiments, okay? And so nowadays we say that in all these systems, physical, social, biological, complexity is exhibited because they operate near criticality. And even there are editorials right now. But this story encompasses about 25 to 30 years. It was not at all easy to persuade people that complexity have anything to do with the phase transition. So our lab study complexity, nature, and manifestation of critical phenomena. Okay? This is, I repeat again, complexity for us is synonymous of critical phenomena unless you demonstrate the opposite. And three paradigmatic examples are three stuff that have to do with transmission of information or energy or whatever. In the left, you have proteins. Proteins are structures that move continuously. When they move, it's because some other protein interact with them and then transmit this information to another proteins, changing the allosteric effect, etc. So we make the hypothesis that proteins, in order to be able to self-function, need to be critical because they cannot be too rigid or too flexible. In the two extreme, very ordered or very disordered, they will not be able to transmit information. This is a paper of 3 years ago demonstrating that that's the case. Mitochondria have also, as you know, are inside the cell, are the engine that drive the energy through the cell. And the mitochondria are healthy, they are critical in the rigorous sense, like we demonstrate in this report. When you segmented the network of mitochondria, they are pathological, like in the case of Down syndrome, for instance, it's a typical case. When you fuse them, you make more compact. Also, they don't work like healthy controlled mitochondria. And finally, the case I'm going to describe today, the brain seems to be in between a disordered regime and an ordered regime, as the data I'm going to show later today. So, as I said, I would like to tease your intuition, develop your intuition, what I'm talking about, with three examples. if I have enough time. The first example is very, very pedestrian and on purpose is cartoonish. I hope that you appreciate that. Let's suppose that you have a bag with buttons, okay? And you have an assistant and you say, please put one hand, remove one button, and then take another hand, remove another button, and I'm going to tie the two buttons with a link, with a string. And then you throw the two buttons inside the bag. And I'm going to have another assistant that is going to take, you're going to count how many buttons appear when I at random put my hand inside my assistant, put the hands inside the bag and remove. At the beginning, I will start with disconnected buttons. So most probably, surely, the number of buttons that my assistant will count will be very small, like in this case. Right? So in this case, I'm plotting the average, the number of buttons, and I keep repeating this many experiments, but as a function of the number of links that I am applying. So it's going to be, of course, a moment in which when my assistant, after many, many iterations of this, put one hand, remove all the buttons, and this is when we are going to be in a phase that we call the connected phase. Every button have at least one link with any other button, so when you put your hand, you remove all the buttons. And this is a phase transition, okay? Actually belong to the percolation kind of transition. And it's going to be a point that will be characteristic, and we call it that a critical point. And I'm going to give you the first characteristic, which is that if you repeat the experiment many times and instead to count only the number of buttons, you compute the standard deviation of the number of buttons, the standard deviation, the variability of the number of buttons that you see for this percentage of links will be maximum. So the variability will be almost nothing at the beginning, almost nothing at the end, because you have 100% of link or no links. But in the middle, you have a largest variability. How peculiar is this? Actually, it's very, very peculiar. This kind of percolation tells you that when you are at a critical point, the variability is the largest, that you have clusters of all sizes, meaning that the number of buttons that you pick up near this value, if you plot it in a histogram, is going to have a power law distribution of number of buttons per belonging to a cluster. And if you choose something peculiar, which is the second largest cluster, meaning the looser, not the big cluster, but the second largest cluster, is going to peak also at the critical point, and it's going to increase with the system size, of course, like the variability. If you make if you put 1 million buttons in the bag at the beginning, you will have much larger variability, like if you put 100 buttons when you repeat the experiment. And this variability will go like a power law, n being the number of buttons. And these are all generic properties of critical systems. If you repeat this, I have to speed up with a model. Instead to have buttons and links, you have trees that burn, and you count the number of trees that are being burned. You will have similar quantities. The variability will peak at the critical point. At the critical point, you will have the largest susceptibility. You have the largest number of configurations, the largest variability. In short, you will have the largest variability at the transition. This criticality, I give you two examples of percolation, can be seen in a more dynamical setting. Let's suppose, and start making analysis with the neural networks in your brain, meaning the analysis in your brain about neural networks in your brain. And so suppose you have a structure, which is the network of streets. You have individual nonlinear dynamics in the driver, a car going around, and now your parameter is the density of cars running in these networks. Of course, you could have a phase in which you have few cars, and let's call it the gas state. You have many cars, you have a solid jamming state, and in between, you have a mix of a gas and a solid, you can have a phase transition. So Why is it interesting to analyze this phase transition of the curve? Because let's suppose that you run, this is a model due to K. Nagel 30 years ago. Let's suppose you compute this in a model in which the only detail you need to know of the model is that you have a network and the car is going to go as fast as possible unless you have a car in front of you. If you have a car in front of you at a certain distance, you will brake stochastically. So if you do that and you start increasing the density of cars, you will see that the flow of cars from a given point, this is density, meaning the number of cars in the entire system, and this is flow, meaning number of cars crossing a point in a highway. As you increase the density, the flow of cars increases linearly. But there is a point in which there is a critical density in which now everybody has to start braking. So if you compare the dynamics of the car here with few cars, the dynamics of the car at the jamming transition is very, very different. Why? Because if you ask about how I care about other cars' speed in the system, when there is few cars and nobody's in front of me, I'm completely independent. I'm completely uncorrelated. So you have a Passonian kind of trains of cars. But when I'm here, the things change dramatically because now, not only that I have to brake, but when I brake, I transmit this brake downhill, to the other cars. So, by the way, this is the point of maximum efficiency for the engineer that designed the traffic network because he wants to have the largest number of cars passing through a point. Okay? He's happy. But the driver is completely unhappy because if you now connect with what I said at the beginning, at the critical point, the variability is larger. So one day you drive from A to B to your job and you're lucky and you reach to your destination in a short time. Next day, you enter in one of these traffic jams. This is a graph of space and time. Each dot is a car, and each of these black things is how the jam moved backward for the critical density. So as I said, the criticality, the variability of the travel time is maximum. The jumps are all sizes, like in the buttons or the fires. You have a power law distribution of jamming. So the probability of being in a small jump of size 1 is very large, but there is a non-zero probability that you have a jump of the size of the entire highway. So these two lessons tell you that the higher efficiency and the predictability at criticality exist and coexist. So these three examples tells you that at criticality, the variability of the order parameter fluctuations peaks at criticality. And also that increase with the size of the system as a power law. So larger the system, larger the variability. You're familiar with the law of the large number. Usually we increase size and we get more averaging. Well, this is exactly the opposite. You have an excess of variance when the system grows. The clusters exist for all sizes, jumps, fires, buttons. These all sizes of clusters tells you that you have long range, meaning non-exponential, slowly decaying, spatial correlation, and temporal correlation. I mentioned to you that if a single driver breaks, at the jamming transition, produce an avalanche of braking behind him that can be transmitted if the density is critical to the entire system. So can have repercussion very far away, and also it will take a long time to dissipate because you have to restart every single car in the jamming in order to dissipate the jamming. And this is important also for neuroscience because you are accustomed to deal with interaction between neurons, short range and long range. I call it interaction to what most people call structural connectivity. Despite the fact that the interaction in these examples are short range, one driver only see the other car, or one button only interact with another button, the links, the length of the correlation is what emerged, can be unlimited, can be as large as the system itself. And these two things, interaction and correlation, okay? Interactions are fixed, but correlations can be easily modified by changing a single parameter, a density of quartz, a temperature, etc., excitability. And the most important thing, these properties are universal. They do not depend at all on the detail of the system. All these transitions have exactly the same quantitative properties, despite the fact that you are talking about quartz, photons, neurons, proteins, fires, trees. Okay, let's start with the caveats. Criticality, what is not? Criticality is not a technique. It's not a software, it's not a tool. It does not solve anything at all by itself. I can guarantee that. And thank God it's not coming on a black box. So when I say criticality, I refer to a commonly observed state of matter, characterized by scale-free correlation, what I was telling here you, that you have long-range correlation that are unlimited, etc., etc., etc. These correlations have no characteristic scale. You cannot say my average correlation is that, because there is no first or second moment characteristic of that example. When you have a criticality, the only characteristic scale is the size of the system you are observing, which you decide, or the length of the observation time, which you decide. Everything else is scale invariant. In other words, what people call fractals. According to several lines of work, it seems that the brain likes to be in such state of being scale-free. So we take inspiration of this to see if we can understand brain stuff. In the 90s, I will give extended explanation of where we have our arguments to go and do the experiments. So we will say that we think that the brain is critical because we know that microscopic complex natural phenomena always result from some collective process of interacting simple nonlinear units. Everything macroscopic have an underlying collective microscopic process of elementary simple units, and that process may exhibit collective phases, what we call phases colloquially, with very different correlation properties. We change the temperature, we go from water, one drop of water in a millimeter cubic, to a gas expanding the entire room. Very different correlation properties just by changing a single parameter. Highly correlated brain dynamics, we know that produce synchronized state with few coding, with a small coding value. And also we suspected in the 90s that if the dynamics is weakly correlated, there's not going to be information flow. It's not going to be transmission of information if there is no correlation across spike trains or whatever. So from these two things, we concluded that the cortical dynamic should be in between, being another example of a phase transition. So finish with this gospel of criticality, and I hope that it's allowed you to develop some intuition of what we are searching from, motivation. In this review, I wrote that the problem of how we built a large repertoire of a spatio-temporal activity pattern is to involve universal mechanism of complex phenomena, critical phenomena, which is evident in any dynamical system poised near a critical point of a second order phase transition. Second order means a continuous, like the one that I showed before. Okay, so let's see how we proceed. So first of all, you have to, at least in our opinion, that's what we did in the almost 15 years ago, is to, I'm lying, 10 years ago, we converted the ball signal into a point process. In this paper, we claim that in a process that is correlated, the only informative points are the extremes. So the rest is just piecewise straight line joining the values with the points. So we claim in this paper that if you only take these few points, you can reconstruct, for instance, the resting state networks, and you can compare with using ICA for 6 resting state, using only the point process. Okay, you get this localization of resting state. In this paper, then we claim that 90% of the ball signal can be thrown away, and what you gain is that you have a sort of a more dynamical, instantaneous information of the process. By the way, these 2 papers from Spore Lab, one just appeared in PNAS yesterday, the other one is in the bioarchive, introduce a technique which is a variation of what we did 10 years ago, actually, and they recognize that. It's a beautiful board that I recommend just to be convinced that the dynamic information is on this point. So for us, the reason why we wanted to use this point process is that now we wanted to define cluster of activities like cloud in the sky. We are going to cluster points nearby in space as clouds, okay? And we're going to count literally these clouds, and then we're going to estimate the size of these clouds as a function of time. So here you have each color for the pixels belong to one cluster, one cloud, blue to another, etc. Okay? And of interest to us, from the point of view of a phase transition, is to see how these numbers evolve. The number of clusters, or the number of clouds, and the size of the largest cluster. We're going to call it the order parameter. Why? Because if the cloud is as large as the sky in Buenos Aires, I'm going to say that it's a cloudy day, it's a very ordered day. Instead, if I have few clouds in the sky separate apart for small size, I will say that the sky of Buenos Aires is disordered. So the maximum size of the largest cloud tells me how ordered is the system. And that's the reason why we call it this 10 years ago brain meteorology, because it will track the dynamical state of the cortex as a function of time. Now, if you plot the order parameter, remember, was this quantity that you see evolving in time, as a function of the active sites, meaning how much stuff is in the sky, independently to which cluster it belongs. So you count the number of boxes that are active, you count the size of the largest cluster, and you put a dot. And these are the green dots for the entire scan in resting state, for the entire ROIs that you have, for the entire brain. And when you do that, you discover this kind of sigmoidal, after you normalize, of course, shape of all your points during a scan for a single subject. Now, also, I'm plotting in the top panel the number of clusters, okay, which is the other quantity, as a function of the active sites. And you see 2 things, that the number of clusters increase, the variability increase. Remember the very few slides that show you about the variability at the critical point, and then decrease, and decrease the variability as well. So this is the percolation state of the critical point that we're talking about, when all these clouds coalesce. And the interesting thing is that this variability is exactly at the point in which the sigmoidal functions start going up, like in the critical transition. Now, but not every sigmoidal thing will be a critical. And in order to do that, you have to quantify the variability over here. The variability is the black thing. And also, you can tell me, okay, then tell me how much is the chance that the brain is around that critical point. For that, you count what we call the resident time, how many points you have in each value of the active site, and you see that most of the time is around the transition, is around the highly variable state. So in conclusion, the spontaneous fluctuation evolve in a continuous state transition, being most of the time near the regime that got the largest variance. Voila. Also, the thing that you like to do is you have to identify correlation. As I said, is the signature of criticality are the correlation. One way to measure correlation is to measure avalanches, meaning how many and how long it goes from no activity to no activity again. And you count the number of voxels in a given region, a given slice, and this you have one avalanche, and then you have another avalanche later on. As a function of time, you count the size of the avalanche, the number of voxels from the beginning to the end, and you plot in a double log plot, and you found that the size of the avalanche, the probability to see an avalanche of sine 10 to the 4 is, probability to see an avalanche of 10 voxels is 10, you see it 10 to the 4 times, and then it goes down in a scale-free manner with an exponent that is what's predicted by theory of 3/2. And each of these dotted lines is from a different subject in a different experiment, always in resting state. The red line is the lifetime, how long it takes the avalanche. It's predicted to have an exponent around 2, because, as you know, Bolt's signals are relatively short, 600 time step. The evaluation of lifetime is not very good. But this is the second thing. This is in 2012 with Enzo Tagliasucci. We published this paper. That was the very first paper on point process applied to these things. So the fourth thing that you need to do, and this is really the nail in the coffin, you have to measure what's called correlation length. It's a very simple property, and I don't understand why I'm having too much trouble in the review process every time that we send a paper using the connected correlation function, which is not the usual correlation function that we are accustomed to in neuroscience, but it's used as a trick to estimate how far the correlation goes into your system. Furthermore, it's not just the Pearson correlation, it's the correlation of the fluctuations around the mean. So you're going to subtract everything that is common mode, everything that is latent, everything that is mean field or global signal, as you call, but you're going to remove it at time t. So consider the record activity x of ti, meaning one time series of Bolt signal at n location, t being the index time, I being the index space. So you transform your Bolt signal x into the signal u by subtracting x of t of I. Remember, I is the location, is the ROI, minus the mean of x of t, time t, of I for all the ROI from 1 to n. So after you discount that, what you have left is the fluctuation around the mean. So then you define the distance between your IJ, meaning your ROIs, in Euclidean distance between locations, and now you're going to calculate the correlation of these transformed signals, UI product UJ, for equal distances. So this delta here means that you need to bin your data into equal distances among pairs, calculate the product, normalize, and you get C of R. This C of R, by definition, because you subtracted, cross zero. And the value of distance for which C of R is equal to 0, the crossing, is the correlation length. Correlation length simply tells you how far apart you have to go to encounter two Bolt signals that are completely uncorrelated. Let's see an example how it looked like. Why is it important to do this? Because we know from theory that the correlation length increases with system size, which is only happening in criticality. And because you have subtracted all the spurious correlation, if this stuff is not critical, this C of R will not grow with distance. This is an example from this paper, 2012. Title was called What Kind of Noise is Brain Noise? we wanted to know actually the correlation properties of the brain fluctuations in the ball signals. So we need to check the correlation length, and we know that increase with system size. Here in the panel on the left, you have many connected correlation functions for clusters of different sizes. Simply, we took the resting state network atlas, the mask, and we took blobs of different sizes. And for each blobs, we extracted the time series. And for each of these blobs, we calculate the average connected correlation function. We look at the zero crossing, and in this example, for the smallest blob, the correlation length is about 5 millimeters. We then look at the file, what was the number of boxes that we have computed that, and we plotted the size of the blob as a function, the correlation length as a function of the size of the blob. And after you do it with all the blobs, the largest, the intermediates, and so on, you have a nice straight line that tells you that indeed the correlation length of the small blobs is small, and the largest blob is large. And the morale is that 2 voxels, 4 millimeters apart, in a blob of 20 voxels, are as correlated as those 40 millimeters apart on a blob of 4,000 voxels. So this is, as I said, is very important to disambiguate if your system is critical or not. You can use mutual information using the same tricks, measure mutual information in small blob, large blob, set a threshold, and now you plot mutual information length as a function of blob size, and you get a straight line. And then you can play this nice trick, because if you rescale this graph, in this axis is in millimeters, and here you normalize the axis by the length of the correlation length you have measured, all the mutual information as a function of distance overlap in a single graph, which means that information, mutual information function as a function of the distance is scale invariant, is scale free. And the only case that that is true is that your system is at the critical point. So it's very strong evidence, but still we have to try to prove this writing a very simple model with a single parameter, which is going to be the excitability of each node. We're going to use the connectome of Hackman 1998 region of interest, and we're going to modify the excitability of each node. This is a paper in 2013, and modifying the excitability of each node in an extremely simple toy model. You have different phases. You have a critical phase with sparse activity. You have a very large neural activity, and you have very low activity at the supercritical point. You can measure the cluster size as we did it in the case of the experimental data. And the advantage is that here we can analytically know what is the excitability that we have to use, okay, in order to have a critical synthetic brain. And then run our statistic, calculate the distribution of clusters as a probability of different cluster size for different conditions, supercritical, the blue is subcritical, the red is critical. And you see that without any fitting, only obtaining the value of excitability at which the model is critical by this definition, the distribution, the experimental distribution of clusters derived from the Ball signal of a resting state subject matches perfectly the distribution in red of the clusters in the model. The cutoff in the model, of course, is smaller because this is a full brain and this is 998 region of interest. So the largest cluster cannot be as large as the experimental. But then we can measure also the correlation length as a function of distance for the experiment, for the model, exactly the same we did in the previous paper. When the model is critical, the red dots correspond to the correlation length as a function of the size of the block, and you see that it matches perfectly without any other fitting. And then when you compare the distribution in space of the resting state networks of the model using 998 regions of interest, you get, of course, for supercritical, for subcritical, and the critical condition. When you compare which one is more similar to the experimental distribution, you found that is at the critical excitability. There is a more quantitative estimation of these similarities in the paper, but the bottom line is that only at criticality the model replicates the resting state experimental data. It's a strong evidence that, first of all, the connectome, which is what we use as our structural connectivity, is important, but only if the model is tuned to criticality, which is not by modifying the structural connectivity, but modifying the excitability of the node, the only parameter in the model, you obtain agreement. Okay, also we should check some honest prediction, again, without fitting. For instance, one thing that we know is that the correlations when you lose consciousness, for instance, under anesthesia, should be decreased. The reason is the landscape or the manifold in which all these trajectories in the brain is a very lousy Wavingham arguments of how energies are distributed in criticality. When you're near criticality, your trajectories are slowly attracting to some metastable points. So your manifold is shallow, it's always shallow. On the other hand, when you are in a far from criticality, these potential wells are deeper, and so it's harder to take you from you are. And if you kick this particle, it will come back faster. So in time, you have trajectories that are going fast to return to the previous state, while in criticality, you have what is called critical slowing down. This can be evaluated by the autocorrelation function of the fluctuations. In the space, we know that because of this landscape that is relatively shallow, in criticality, here I make a sort of cartoonish representation. This is in the paper that I'm going to mention later. I make a cartoonish representation of what is the structural connectivity, meaning node A is connected to E, to D, to C, and to B through different weights, different potential barriers. And so, because this is shallow, the probability that when you observe functional connectivity, you're going to see sometime going to C, sometime going to E, sometime these are the functional connectivity or functional correlations that you observe. Under this circumstance, the functional connectivity will be less variable. Again, the variability will decrease, and the long-range correlation space in time will decrease if you go away from criticality. This is essentially the picture that parallel the view of Giulio Tononi about consciousness, in which at criticality you have a mix of segregated and integrated. If you lose consciousness, you go to the segregated state, which is what we are saying here. Let's see how we play this game. So this is a paper in 2015 in which we analyze propofol-induced loss of consciousness, and we predicted that the correlation should shift, okay, in the way in which I explained it just a minute ago. Meaning, you should see that if you compare the variability of the full repertoire at hand, given by the structural connectivity, which you know, because you have the connectome, you compare with how many functional connections you have detected in your across your experiment, and in the wake state, you have larger variability, larger repertoire as a function of the link density. This R is just the ratio between the structural and functional, meaning the number of structural connections that can be seen during the activity, and during the loss of consciousness, this repertoire is decreased. You can do the same analysis for different network nodes. You can take the ratio between the two and start playing this game. So the prediction about the decrease of the repertoire is correct. And now if you want to see how the temporal correlation behave, you just choose your favorite Karsh exponent with the tender fluctuation analysis or the wavelet Karsh exponent, or just simply measure the low frequency power of fluctuations of the Ball signal across the whole brain, and you'll see that there is what I call a bleaching. There is a shortening of the Ball correlation, temporal correlation during anesthesia, and this is a statistical significance between the wake state and the loss of consciousness and the recovery state after the anesthesia. So these are the kind of game that we play, motivated by these things, inspiring criticality. I have a few minutes, so I will run over two other things that need to be consistently observed. The same correlation laws should be true at smaller scale. So everything that we say, if you go to the microscopic case, should be seen. The 3/2 power law of avalanche was described in 2003, etc., etc. So, and if you go to even a smaller scale, this is a optogenetic 2-photon recordings in behaving mice. You have rasters of hundreds of neurons as a function of time in a freely behaving animal, which is being recorded in this case in the visual cortex, while it's seeing some stimulus or a resting state. And the prediction is that at that point, you should have to compute the connected correlation function as a function of the size of your field. This is a paper that is being reviewed by Thiago Ribeiro and Ilmar Plens at NIH. We are collaborating in this context, and you see that the zero crossing of all these connected correlation function, independently of the stimulus type, move to the right, as the theory says. If you repeat it for the visual cortex or for the auditory cortex, and you collapse all the functions, as I showed before in a previous slide for the Ball signal, all of them collapse in a single function when you normalize by your correlation function, meaning that the fluctuation that you observe in this half a millimeter scale, notice that we're talking about 360 microns here, behave like in the large scale of the Ball signal. Finally, we have recently published a report in which we play this game, which is, I think, will never work unless the brain behave or the neural network behave close to criticality. We know that the temporal correlations, you can evaluate it as the first autocorrelation coefficient, goes to 1 when the system is at the critical point. I told you that the landscape is very shallow, so things slow down. So the activity always is correlated with the previous time step. It was never, even in Ball signal, which you will tell me that the modulonic function filter everything. Even in the Ball signal is corrected. Even in the optogenetic data set, the brain is always trying to repeat what it's doing before. There is a very strong autocorrelation. At the critical point, this coefficient is 1. So I can have a maximum. Uncorrelated, subcritical, supercritical, the thing goes to 0. So I can use that as a control parameter to bring the system to criticality. And this is what we've done in this paper. We will start with different excitability and pushing the system to the critical excitability such that autocorrelation is maximum. And when you plot the order parameter based on excitability, draw this very nice sigmoidal function of a second order phase transition. And the order parameter goes down to this sparse activity, low rate activity in this neuronal network. So this idea of that you can control a neuronal network near criticality by simply using the autocorrelation, the temporal correlation is very powerful because it is my intuition that many of the subcortical regions are basically modulating through very slow neuromodulations, the excitability of the cortex responsible for maintaining the criticality near this optimal region. Finally, universality. I will take only 2 more minutes. We have went from phases, from the concept of phases, which is at the center of physics. Remember the Big Bang? We were in a very hot plasma, and we have to go through phase transition to collapse into a gas, into what is called condensed matter, to see around what we see. So we went from this concept of phase, and everything around us is explained in terms of phase, to the microscopic realm of optogenetics. And now I'm going to show you that these universal concepts apply if you compare your brain with rain. And it must be like that, because as I said, the dynamics of complexity is independent of the details of the system it's composing. On the left, you see the brain phase transition that I showed you before in bold, with this high variability at the critical point, and most of the time spending around the critical point. On the right, you have the percent humidity at many, many regions in the Pacific, 10,000 regions. This is from a paper in 2006, but Ole Peters and Nearing. And on the vertical axis, you have the amount of rain, the precipitation, normalized, of course. And the humidity is low, there is no rain. Makes sense. When the humidity is very, very high, there is a lot of rain. And intermediate humidities draw this sigmoidal function here. Of course, each dot and each cross is an average of many days and many points inside an area of these 10,000 areas in the South Pacific. What is amazing is that when now you plot the variability across 1 year of the amount of rain, you have this curve, which is the variance square of the amount of rain. That means that at the critical point, the variability is large. One day it rain a lot, another day rain nothing. So imagine that if you are a meteorologist in a region that have 67% humidity, the probability of being right is very low, right? Which could be a summer student project. Check the percentage of good hits of meteorologists in the United States for different regions. And in this graph over here, you have a third quantity, which is the amount, and how many times, this little curve here, how many times the atmosphere in the South Pacific is it's at 0% humidity, how many times is at 70%? And you see that most of the time the atmosphere is around the critical point, exactly that we observe in the brain. So these similarities, in a sense, are another proof of the power of universality. So summary, I have shown you, or I have tried to increase your intuition that there are some general properties, universal properties, which you can see in the brain, you can use to design experiments and to test some predictions, that the long-range correlations exist in space and time, that the correlation length scale with system size. I have no time to show you about all the properties listed here. Scaling of the cluster size, distribution, the avalanche size scale with size. The model replicate the observation only at criticality, that implying that the connectome is not enough to understand the dynamics, no surprise. I show you how how this, just as a simple one of the things that we did, how this correlation of bleach when spatial correlation shortened when you lose consciousness. Also that all these properties should be seen exactly the same at different microscopic scale. And finally, that you can adjust or control criticality using simply the autocorrelation, the temporal correlation properties of the mean activity. I hope that, thank you for the patience, and thank you very much. And this is the list of collaborators.
Thank you. That was quite the tour de force. Very, very interesting.
52 minutes. Sorry for the.
And there's your network. Yes. Do we have any questions? I can ask a few. I see that Armin has a couple in the chat room. If others have questions, please feel free to enter it into the chat, or if you want to talk, let us know and we can unmute you. Just wait a second. One question I had, I'll just kind of jump in, is in terms of the, I just was wondering how much, we've been looking more recently at sort of spatial variability, so changing nodes, right, over time. And I was wondering if you had, I mean, I know you obviously the cloud size kind of gets at spatial aspects a little bit, but to what degree are you, can you incorporate spatial variability inside the size or the location of nodes over time into these kinds of models? I'm sure you can extend them, right? And I was just wondering if you had thought about that kind of issue.
Well, that will be related to this proxy, because many of the things that we claim that we need to measure are not possible in a brain. If we focus on the ball signal, for instance, in this case, we make a very simple hypothesis consistent with criticality, in which the landscape of the structural connectivity profile, meaning like the histogram of the weights of structural connections in a given moment in the brain, is always shallow. And that during the dynamics, if we know the structural connectivity more or less, which is this tree that you see over here, for a given node, we can play this game and count how many times we see a strong correlation between point A and point B, compared to how many times we see from point A and point E. So it's like the ratio between what tells you the structural connectivity, what is the repertoire at your disposal, and what you see during the dynamics. And in that sense, it would be nice to see, for instance, how different nodes of different networks, for instance, how inside the default mode network, how much is the divorce between structural connectivity and functional connectivity compared to, for instance, the visual areas or the primary areas of the auditory resting state. So this is telling us about the flexibility of the system. And this is inspired in this kind of pictures of that the correlations emerge in a cooperation between the arousal, which obviously is shifting, and the underlying structural basin of attractors, if you like. I don't know if that is in the line of things that you are.
Yeah, I think that partially gets there. I was kind of thinking also of like, so if you think of using regions of interest, right? You know, that's sort of an a priori sort of fixed assumption that the regions of interest are in fixed locations, right? And that there's no movement there. The nodes are kind of fixed. You know, one of the things we've been looking at is sort of multivariate spatial evolution of networks, right? So networks kind of change shape and size, and there are multiple overlapping networks, and so it's kind of a different framework, I guess, than what you're doing, but would be interesting to think about.
Let me interrupt you, Vince, because it's important. The analysis that I just suggested is not tied to a definition of the node. This node that I call A is just a spatial location in your brain. So it is parcellated not in terms of resting state or function, but it's just one point in your brain. It's a 1 centimeter by 1 centimeter square of your brain. And I agree with you that from this framework is going to be different networks evolving in time. And that's what I like, because these blobs are coalescing and are dissipating in time, forming new networks of different partners. The question is, we have the structural connectivity between these nodes. We should use it in order to define a proxy which consider not only what you call functional connectivity, which I call correlation, but what we call interaction, which we call structural connectivity. So I have not seen, except in this paper we published a couple of years ago, an extensive use of this concept, which is the ratio of the repertoire and how much you use in the repertoire. And it's a beautiful information because it's telling you how much the spontaneous changes in arousal are changing, and it's very different in different regions of the brain.
Great. Thank you. I won't take all the time. I would love to have a beer with you at some point. Lots of things to chat about more in more depth. But Armin, did you want to maybe ask your question since you're on, or if others wanted to pipe in, please do. So yeah.
Sure. I will start with Matthew Mark question because I can follow up later. So the question is, shall we describe the resting state brain as operating in criticality, or is it oscillating around criticality?
That is a very good question, because when you see the data, it's obviously oscillating around criticality. You see that if the critical point is around the region of large, I hope that you see that, right? You see the graph? So the point of larger variability and the knee of the sigmoidal indicate around the position of the critical point. But this axis is logarithmic. It goes from 100 to 10,000. For God's sake, this is really highly variable. And I like that. I like my brain to be very variable. I don't want to have a brain that's always centered into exactly the same number of units active. It will be impossible. In the same sense that the atmosphere at large scale is meandering around the critical point, the last figure they show. So that's the technical answer is, yeah, the state of criticality is a very wide region in which you always come back.
Great.
So I had the same question related to this. So most of these studies that look at the avalanche or a couple others, they look at that specific time point, like they choose those specific time points. But we do not look at the other time points. So if we are in the oscillating between oscillatory, what about those time points?
I don't follow your question, sorry. Maybe I am not hearing well. You said that most of the...
So we look at the specific time point and those avalanche time point and critical time point, and we show, they demonstrate or they illustrate brain networks, right? Like, for example, yes, by choosing, for example, threshold in the intensity.
Oh, no, you're talking about, I'm confused. So, sorry. When your question is referred to the definition of these points, right?
Correct. And I'm asking, how about the other time points?
Which other time points?
So here you choose some with the red and you choose them as a crit avalanche point, right? As a critical
Yes.
time point.
No, these
So-
are not avalanche point. These are, there is a problem of definition. Sorry. First of all, don't call it avalanche point, because avalanche point means a sequence of points in a space and time. These points are a point process which is defined for each time series. So you have a ball time series in a single location. You define for that single time series of a single location, you transform the continuous time series in a point process. In the same way that in the 60s, neurons were converted into point process because action potentials were known to be all or nothing. So people say, I'm going to take just the point, and you deal with point process. It's much simpler. And what we show is that if you take this point process, you can reconstruct the resting state, meaning you are not losing information. Later on, we understood why this is possible. Okay, it is simply because the rest of the signal is strongly correlated between this point and the negative point, meaning the valley. Between the valley and the peaks is basically a straight line. So as long as it's correlated, you can replace the entire signal by these simple points. Now, you can ask me, Dante, if you change the threshold, you go from these points, okay, to other points that below the threshold, okay? Then you have to consider the other little points over there, right? So in that paper, in 2012, you will find the reconstruction of this resting state for different thresholds, and you will see that the amount of information, the new information incorporating these little points is very little. Okay? It means that the modification of the threshold change your reconstruction or whatever you are doing very little. It's not drastic. And this argument is now used by Olaf Sporn and his group in these two papers to do the opposite process. They just take the product of two time series, and now they have n times n time series, which they call H time series, because it's the product of this time series against a time series in another side. So they have n times n H time series, and for those time series, they recover the information. Basically, it's the reverse process of what we did. And they say that if the threshold is 0, they can reconstruct essentially 100% of the functional connectivity. As the threshold move out of 0, you start losing. So it's a little technical, but I hope that your question was about this. Is okay? That was. Thank you, Ming.
So do we have time for 2 more questions? If it
I
is
have
okay.
an entire afternoon for me.
So I'll ask both questions. Juan asking, is there a role for actual neuroimaging to identify brain nodes that are more critical, pathologic for the system? And
Can you repeat the beginning of the question? My audio is not very good.
So the question is there a role for actual neuroimaging to identify brain nodes that are more critical or pathologic?
Okay. So let me repeat the question just in case. If there is any rule or any law or any trick to identify ROIs that are more critical than others, well, this is an excellent question. I hope you do it. Send me an email when you do it, whoever is asking, because it's related to what Vince was asking before, and or at least I understood what. In this hypothesis, okay, you can test what is the average ratio between structural and functional connectivity for each node. And I use the word divorce because really what you see is that in some nodes, there is nothing to do with the structural connectivity. And in other, there are exactly what the structural connectivity tells you. It is long known that part of the structural connectivity is exactly the same like the functional connectivity. What you see in the connectome is what you see in the functional connectivity. So what we have introduced in this paper is a way to draw for each node as a function of density of links, meaning as a function of changing the threshold, how is that divorce? So the distance to criticality will be this ratio, or some, let's say, Kolmogorov-Smirnov distance between these two, okay? Which is what is being plotted here. So I advise whoever did the question to go read this paper in 2015 in the Journal of Royal Society, or if you run into trouble to implement it, I can send you the code, and then you can know you have a proxy of how critical a node is, how rigid or how flexible or how in between. And it's a very simple measure, and it's rooted into what we know about the physiology.
Thank you. So there are so many questions. I apologize because
Please, I love that. Don't tell me that we don't have time for questions.
So we can follow up on the Brain Slack. I will. We have a specific channel for your talk. We can probably follow up there. What do you suggest, Vince?
Yeah, I think that's good. Maybe we can finish up with one more question if there is one, and then we'll continue the discussion on Slack, which gives us a plan. It also enables other people to see the questions that are asked and the answers, and so can be helpful over time, I think, for new people that come in.
Sure. So the last question is from Gopi. Does the brain operate away from criticality in mental health disorder or not?
That is a tricky question because we don't know anything about mental health disorders. We call it mental, but we are so far from there. If the question is, do I know of any paper in which the so-called mental disorders use this type of framework? Yes, there is a few papers, and please just Google your favorite disorder together with brain criticality, and you will have it. Personally, only we have dealt with, if you can call mental disorder be under psychedelic influence, we have a couple of papers, one in psilocybin, the other one about LSD, and this is work done by Robin in Imperial, now in Hammersmith in UK. So all the literature on psychedelic have been influenced by this kind of work. Personally, I have not worked so much on that to give a straight answer.
Thank you, everyone. Thank you, Dr. Shlovi. So please ask your question that we haven't answered yet in the Slack channel. So we can continue discussion there. And it is a very interesting topic. So we probably can have more journal club and presentation in the dynamic analysis group leading by Robin Miller. So we can follow up on more discussion on there too. Thank you.
Thank you, Dante.
Thank you guys for this
Your time.
initiative.
Yeah.
Congratulations for this initiative. Really, it's an honor to participate.
Thank you very much. Thanks, everyone, for joining. Take care. Stay safe.